remembering that we're humans, we are neural networks. We're all neural networks, whether you like it or not. We always have a brain. So just as neural networks have two different modes, one is the training mode, which is where the neural network is taking in new inputs and updating its weights, and the inference mode where it is just doing things. I like to say we should try to focus a lot more on the training. We should try to get our neural networks to be more in the training mode and keep learning, always be learning something new, always update your weights.
All right, so hello everyone, and welcome to the AI Stories podcast. I'm Neil Leiser, I'm a data scientist at Iwoka, and I will be your host. So today, our guest is Yan Su. Yan first did an MEng in Civil and Environmental Engineering at Imperial College London, and during his MEng, he also did an exchange program at the University of California, Berkeley. He did a few internships in consulting and engineering, and in 2019, he actually joined DeepRender, a startup developing the next generation of video compression technology using AI, where he is now currently a senior machine learning engineer. So this episode is actually kind of a special one because Yan and I are both really good friends from uni. We did our bachelor together. And so I'm really looking forward to this conversation, which is going to be super interesting. We're going to talk about our studies at Imperial College London, the transition from engineering to the world of data science and AI, deep learning applied to video compression, but also give advice on how to progress in your career. So if you enjoyed the episode, don't forget to subscribe to my YouTube channel, AI Stories, and follow us, so me and Yan, on LinkedIn. All right, and let's start with the fun bit now. Hi, Yan. How is it going? How are you today?
Hi, Neil. Thanks so much for having me today, for inviting me to your podcast. Great one. I've listened to a couple of episodes so far, and very interesting people you've had on board. I'm humbled that I'm one of those myself. And so, yeah, I'm really looking forward to our chat together, given that you and I pretty much come from the same suit. So yeah, we're very excited for this.
Thanks, man. Thanks. Yeah, looking forward to this conversation. And yeah, let's actually start with the bachelor. We both did the same bachelor. You come from Sweden. I think you grew up in Sweden, actually, and then moved to the UK and then decided to study civil and environmental engineering. So yeah, just why did you first decided to study civil engineering? Like, what was your thinking behind this? And yeah, why this bachelor?
Yeah, so it's actually got a funny anecdote behind it, but I guess to start off with is pretty much the standard story, like like most engineering students I know, super fond of subjects in school, like maths and physics. I went to this natural science specialization type course in high school in Sweden, and really, yeah, got fascinated into. I've always really had a knack for sort of physical, so natural science subjects, and so I knew that I wanted to do something in that space, but I also wanted to do something. I didn't want to. I didn't want to see myself being in the lab, in kind of without actually interacting with the outer world. So I wanted to do something applied and actually meaningful for the subject that I was going to study. So the obvious choice was engineering. I thought of going abroad I had plans on studying abroad during my sort of last year of high school. I figured I wanted to sort of reach out, expand my horizons a bit, and I felt quite comfortable with the idea of going outside Sweden and meet new people, meet different cultures. And so I started applying to some places in the US and the UK, and I ended up at Imperial College London. So yeah, you asked why civil engineering.
Yes.
So specifically, why civil engineering? For me, it was actually a massive translation mistake. So in Sweden, when you say the literal translation of civil engineering, which is civilingenjör, what you're referring to is a master's of engineering. So that means a 4-year or 5-year course in engineering. So you can be a civilingenjör in chemical engineering, you can be in mechanical engineering or computer science. And so I didn't really clock that when I was applying to the universities. So I picked out of the list of Imperial courses in engineering. Well, there was civil engineering. So I was like, oh, okay, yeah. I mean, this is sort of what I wanted to do anyways, if I applied to some place in Sweden. And I got in, and I was quite baffled the first week when I walked into my first lecture of geotechnics and soil mechanics and having to, and I realized then what civil engineering was actually specifically the engineering for civil structures such as bridges and buildings and infrastructure. So I was kind of a little bit taken aback there. Maybe you could argue that younger Jan should have done a bit better research. But it was actually quite fun in the end. Then during the engineering course, which is a 4 years integrated master's course, I realized very quickly that coding was what I really fell for. So in civil engineering was we had this MATLAB course. MATLAB is this coding element in most of civil and mechanical engineering. Every undergraduate in civil and mechanical engineering will have played around with MATLAB at least once in their lives. And so I realized quickly that was what I wanted to do. And so I started to dig much deeper into the coding world, and started to take courses on the side and sort of eventually sort of try to steer my route into sort of computer and software engineering, and now in deep learning and AI. So yeah.
So is that how you transitioned from civil or for engineering to data science and AI? You first got those coding courses, and you got more and more interested in coding and I guess in AI, and then you slowly did the transition?
Yeah, I think as being interested in coding during the late sort of 2010s, really when the AI revolution was kind of started to kick off, it was almost impossible not to realize that, not to sort of notice that there was something going on around the spaces of artificial intelligence and machine learning. And so those things sounded quite interesting. It sounded quite important to me, and so I figured I needed to learn about them in order to stay relevant with the current technologies. And so yeah, I started to look into it. But at that time, it was more specifically just coding in general, just playing around with Python and Java and just getting a bit more and doing a few side projects on my own. So at that point, it was still quite, I guess, the idea of getting into the space of AI.
Okay, so that's how you basically did some extra courses, did some side projects during your civil engineering studies, and that's how you started to learn about AI and machine learning.
Yeah.
All right, and so you've kind of done all this degree in civil engineering. Now you're interested in AI. So what do you think about this degree? Do you think it was worth it in the end? Or do you kind of think, oh, why did I do civil engineering? I should have done maths or something else. What are your thoughts around this?
Yeah, I guess, so I think especially for for people who are not familiar with the UK higher education system, is that once you've selected a course, you are pretty much fixed. You're pretty much sort of predestined to a path. You can't really choose the courses, your curriculum, in the same flexibility as, for instance, what I did when I went to the United States from a year abroad. So yeah, I mean, I think I definitely could have used less time studying soil mechanics and concrete, and I believe I probably would have achieved a lot more if I had gone to a pure maths or a computing or physics course in terms of kind of where I am right now and what I'm doing. But yeah, I mean, as a civil engineer, you also pick up a lot of transferable skills. Such as obviously you have basics of coding and of course mathematics and statistics, also fundamental, both for civil engineering and for machine learning. So a lot of the things that I see today are actually were taught in a civil engineering maths course, for instance. So and I also think just generally the idea of problem solving is what you eventually pick up from your engineering course, and which can be transferable to any domain that you end up working with. So absolutely, I would say that civil engineering was formative to a certain extent. And I guess, you know, in the end, it's not, I realized kind of, you know, in retrospect, I guess at the time I was a bit sort of, disappointed in my choice during the time, but looking back now, I realized maybe it wasn't so bad as I probably had made it seem back then. You know, people always change their minds about the career during uni and afterwards as well. And so I guess ultimately, I think every experience is a worthwhile one, in my opinion. And I also had a great friendship group coming out of that degree, as I believe you must understand quite well.
Exactly. We wouldn't have recorded this episode without this bachelor. But yeah, I also think like lots of skills are transferable, and like civil engineering really, it teaches you how to solve problems in the end. And in AI and machine learning, that's also what you do. You have a problem, you have some tools. Sure, you need to learn the tools, but in the end, you need to solve problems. And I think the engineering part was, at least for me, much more challenging sometimes than AI. So I feel, yeah, it was quite useful to go through those very challenging problems, solving them on your own with lots of rules, lots of things you need to think about. And maybe it also gives you another perspective on AI and machine learning compared to someone who did computer science or math. So I'm, quite happy with the bachelor. Although if I had to redo my life again, I would have chosen maybe something different. But yeah.
That sounds like a familiar. I've probably said those exact same words.
Perfect. Yeah, sounds good. The only problem is I can't redo my life at the moment unless you come up with some algorithm or something. Maybe next time.
Some Groundhog Day kind of thing. But yeah.
But yeah, no, cool. So I want to continue on this transition. Like you mentioned, you did some courses and you taught yourself some projects. Can you go in a bit more details? Like how would you advise, or what would you do if you were someone who had to start machine learning from scratch? What was your experience and what would you advise to other people?
I think so. For me, I always think that education really can come from anywhere. It really doesn't have to come out of a lecture or a course or anything. It really comes from just you going into going in with a mindset that you are going to pick up information from really any source. And I think especially with a subject like AI and machine learning, both obviously are concepts that deal with the digital world and digital communication and so forth. Internet is just a great. It might sound trivial as an advice, but I think it's often quite understated that literally all of the knowledge is a Google click away. It's a Google search away. So you can access that by always keep a mental note of if you really are interested in that space. There's really nothing that stops you. There's nothing that says that, but just because you chose civil engineering or any other subject for that matter. I think you also mentioned that you also put it quite well that sometimes actually having a different viewpoint, coming from a different background and having a different viewpoint is important for that subject. And so it's really about keeping an open mind and staying and actively searching for the things that you want to learn. And so on the internet, for instance, there are a bunch of great online courses on machine learning and deep learning. Coursera, you have Udemy, you have I can't really think of more. I mean, for instance, I learned I learned coding on Python on Code Academy, where I spent a few weeks of my life and just like taking up how to code in Python, get fiddle with HTML and CSS as well, like on front end stuff, doing some anything really, like and I think also there are textbooks as well, and YouTube videos explaining certain concepts as well, also are great sources of learning. But ultimately, I think it comes down to really want to commit to this space of AI. And if you're not coming from a formal background like myself, having done a master's or in machine learning or AI, just kind of self-teaching yourself, then it's about kind of getting into the just taking on projects and I guess we'll touch more upon that once we get into my year my year abroad at Berkeley, where I actually had a lot of the opportunity to take on projects within computer science and machine learning, and devise my own curriculum into the direction that I wanted to go.
Yeah. Let's touch on Berkeley like very soon. But first of all, just wanted to say, and I mean, it's funny, we have kind of the same background and same kind of career. So I also feel the same as you, like learning by doing some classes online. And I think actually the most important is really doing projects. Like that's really how you can take like 1,000 courses, you will learn other things, but in the end, it's when you do a project that you really struggle, that you really look online, look at Stack Overflow. That's really, I feel, where I could really learn Python, learn AI, learn machine learning. And every time someone asks me, I want to learn about AI and machine learning, sure, there are loads of good resources online, which I share with them. But in the end, like you don't need to be an expert, just start by doing a project. And I feel that this can, I learn most of the things I know by doing projects and maybe less through classes. Although classes are always good, I feel you learn so much more by doing a project. I don't know what you think.
Yeah, for sure. And I mean, you yourself, I know that you did a year abroad in Australia and University of Queensland. So I probably a lot of what I'm saying and what I'm going to say about my year abroad will resonate with you too. So yeah.
So tell me about this year abroad. So for people who don't know, during the final year of our program, we can actually apply for a year abroad and go somewhere else essentially. And Jan got accepted to Berkeley, which is quite a challenging uni and difficult to get accepted. So tell me more about this experience and what did you do here and how did you learn more about AI and data science there?
Yeah, absolutely. I guess as first thing to say is probably like once I got there, I really took the chance to take as many computer science related courses as possible. Try to steer my the university or Imperial year abroad coordinator and try to convince him that no, this is civil engineering related. Don't worry, this is. So it was really the first time I could actually freely choose my classes according to my own interest, and so I took some. I remember I took some data science courses in the fall semester, and then a couple of computer science courses as well. And so really got involved with a lot of there was a lot more Python now, and and actually a little bit of C too. And so I also got involved in group projects where we applied machine learning and deep learning models for problems, so for, I guess, for sort of student projects, if you will. So and that's when I kind of like learned how to collaborate with people in this space, and how to sort of how to, you know, how to theorize about what your model is doing, and to come up with the best way of tackling a problem, for instance. So we had, for instance, a couple of projects dealing with predicting garbage patches in the Pacific Ocean. Another one that dealt with predicting traffic accidents using sort of geospatial data. And so there was basically a lot of variety in courses that I could take, and really sort of kind of propelled me deeper into the sphere of machine learning and data science. I still at that point hadn't really figured out exactly what I wanted to do, but I definitely thought what I was doing at the time was really cool, and I wanted to keep on doing and going on with it. And yeah, and I think the master's project as well that I select. So with our year abroad, we also have a master's project, which is a longer kind of dissertation-like project that we're writing up and submitting. So one of the requirements for a master's for a master's degree. So I tailored my master's project to have as much coding as possible as well. So what I did specifically was I worked with 2D SLAM. SLAM stands for self-localization and mapping. So so the context of this project was to develop an autonomous drone system to detect defects in infrastructure, such as, for instance, cracks in concrete buildings, obstructions on railways, power lines, etc. So I dealt with an aspect of that project, which was the SLAM part. So I built a prototype. Unfortunately, not an actual drone. That would be really cool, but I didn't get as far as for my project. But I had a little 3D printed box that had all of the sensors that a drone would theoretically have. So it would have, let's say, like a LiDAR, which is a laser rangefinder, and an IMU, which is an inertial measurement unit. And so, but without the GPS. So the point of SLAM is that you need to devise an algorithm to try to estimate the position of the drone as well as the map around it at the same time in real time. So at that point, you get a bunch of sensor data, then you need to process it on the fly through certain models. And so I got into Kalman filters, which is a linear Gaussian model, to perform state updates. And you have and so really pulled me into a lot more and a lot deeper into these sort of, I guess, virtual models and much more closer into coding. So yeah, it was super fascinating.
Sorry, so to summarize, you had to develop a drone which would detect like issues within a building, for example. So, or there is a problem with some concrete here, or there is a problem with the foundation there, and then send an alert or something like that to the user. Is that right?
Yeah, so that was, I guess, the scope of the project, the larger scope of the project. So my particular piece of it was more to do around how to localize the drone, so that the drone actually doesn't, slam into the building or literally slam. But yeah, so there were multiple aspects. For instance, the object recognition, which actually was done through a convolutional neural networks, which is something I work with every day, which is fun. But I didn't do any of that at the time. Yeah, there are multiple other aspects, such as the path planning aspect as well, and yeah, a bunch of other stuff really. That was yeah.
So is it to make so first of all, you need to make sure your drone doesn't bump into a wall, as you mentioned, but is it also, should the drone understand where it is located in the environment? Like, okay, here I'm in the sky on top of the building, here I'm on the left of the building. Is it what you mean by knowing the state or the localization?
Well, exactly. If the aim is to localize where your cracks are in the building, then first of all the drone needs to know where it is itself, and then also need to localize where the crack is. So absolutely, the position. It's all about position, and well, as they say, it's location, location, location. So.
And how do you train such an algorithm? Like, how do you say? I mean, surely you have some training data and you say, okay, here you're on the left of the building, here you're on the right, but it should be very precise. So how do you train those kind of algorithms?
So this wasn't per se a machine learning approach. So this is more of a kind of a traditional, you have a state vector that contains the current you track the position and the velocity of the device at that current. So I will say device because I didn't use drone, but like that device, and then you get an update from your sensors where it thinks it's heading towards, like which direction. So you have two different sensors. You can actually have multiple different sensors that can tell you that each can tell you a different thing. And so the question is now, how do you combine this information and deal with the uncertainty from each of these sensors, and to get the next best estimate of the position. And so the challenge of this was really to do this without a GPS, because a GPS would be quite nice to have, which would give you it wouldn't be perfect, but it would give you a really good absolute reference point to where you would be. But you can't expect the GPS to work at all times, especially when you carry the drone, when you have the drone carrying out its work in spaces where the GPS, for instance, don't reach you, for instance, with large high rises and so on. So those were some of the challenges that we were facing.
Okay, cool. So you do your integrated master at Imperial College London. You do your year abroad at Berkeley, and this is where actually you really get into the heart of AI, right? Do loads of projects. You do your master thesis on object detection, and I mostly path recognition, and that's how you actually start to, I guess that's how you actually realize that, okay, I want to get into this world, I want to start working and join the world of data and AI. And so you actually start applying for jobs. The problem is you have a master in civil engineering, you don't have any AI or data science master, you don't have any PhD. I personally did a master, so that this is where I guess our careers are slightly different. I did a master, but you didn't. So how challenging was this to find a job in AI when you come from a civil engineering background? You have no master, no PhD.
I definitely think, when looking back, I definitely think of myself as having probably one of the more unconventional paths into AI. As you said, I didn't have a formal degree in machine learning or AI. I guess for me, it was just at that point, just interest and genuine curiosity. I knew kind of at some point during my degree that I didn't want to do civil engineering. And I mean, it just all credit to the subject. I mean, I think it's a fantastic line of work. But I tried an internship out one summer, and I just felt it wasn't really my cup of tea. And again, it was really the coding aspect that really pulled me, that evoked something, a specific interest in me. So I guess at the time of me finishing the degree, I guess I was in a position where I really wanted to take on sort of any coding job that I could get onto. So I think I shot off applications everywhere out on LinkedIn and Glassdoor. I interviewed for a couple of IT consulting jobs. I got offers from a couple of them, but relatively low-paying jobs, specifically if you're talking about London salary in tech. But I was at that point, I was literally ready to take anything. I just wanted to have somewhere to start off with, and then progress kind of like throughout my career. into a space that a place that I wanted to be. And so I did consider also doing a master's degree like yourself in computing. I figured out that at that point I kind of just wanted to get going with work to see if I, liked it at that point. I think, I probably would say I had a little bit of a mini existential crisis at that point. And but yeah, I think, I sent off CVs everywhere, including, I should also maybe mention I took, at the same time, also following the kind of advice that I gave, I took all the online courses I could find. I followed up with some computer sciences courses from Berkeley. I did a lot of the Coursera courses on deep learning and machine learning. I uploaded the code of past projects on GitHub, on my GitHub, and linked it in my CV. And I think that actually is what was a very important element, because then, so one day I get a phone call from Arslan Zafar, so one of the co-founders of a company that I just applied to called DeepRender. He asked me to come in for a meeting, and they give me the initial pitch. They just received seed funding, and we're now we're about to take on our first employees, and so come join us to do this, to reinvent compression. And so I think definitely, I think at that point they also mentioned that they had seen my GitHub repository and was quite impressed with it. So impressed with the coding quality. So I definitely think that really was the one thing that sort of proved that that I was capable of doing the job. And so I prepared a lot for the second stage interview, which was an assignment, both a theoretical and a practical with coding. So I prepared every day for it. I think I just went all in for the job. They gave me the prospect of this new revolutionary idea that involved deep learning. So and I figured, okay, this is it. This is the big break. This is like the business model makes sense. It holds up. And here they are, like looking for the first employees, and they don't seem like madmen. So I just went all in for this job, prepared for it, and I walk in on my second stage interview, and since I am here, I'm not gonna say that I botched it, but it didn't really go very well. I think I screwed up most of the theoretical part, kind of signifying that I didn't actually have that. It's a really tough job. It's a really tough subject to, I guess, in my sort of self-defense. But yeah, it really didn't go quite as intended in the theoretical aspect. But then we did the practical part, and then they thought I was pretty good at coding, so just ended up taking me, really. And so yeah, I guess in summary, where my journey had been there, it was sort of, I think normally they say sort of half persistence, half luck. I think for me, myself, it was probably a bit more luck, since there was just this job that was in a position to take on people like me, people who didn't necessarily have a lot of credentials to back up it for, but just someone who would just know how to do the job. So I think I ended up roughly, I think maybe that saved me 2 to 3 years of time of progressing in my career up to this point. So I think I was extremely lucky that I managed to save in on this time.
Cool. And now you're senior machine learning engineer, so we can see that you've done well, and that they were actually right to hire you. Maybe you didn't get as lucky as you think, but I think you mentioned an interesting point on having the project on GitHub. And I spoke with Nixon a couple of episodes ago. He wrote a book on Ace the Data Science Interview. And he said something, well, in the book or when we talk, I don't remember exactly, but he said that a project without a link is like a project that doesn't exist. Like you can have 10 projects. If you don't share them anywhere, don't put them on GitHub, don't share a link in your CV, this project doesn't exist. And yes, sure, you can talk about it, but will people believe you? We don't know. So I think that's a great advice, to put things on GitLab or GitHub, share them in your CV? Because actually this helped you to get the job, right?
I do think I do really want to emphasize that point, because at the end of the day, what we are doing 80% of the time is coding, and everything, or every output that we that we produce is based on the quality of our code, and having that code available really says so much about a candidate in terms of the way that they code, and like what types of what type of algorithms that they use in order to, do they do this thing with a naive for loop, or do they vectorize things? And so you can get a lot of the way that the person is thinking by just looking at their code, and I think it's just so important. So I guess first of all, like make sure that your coding skills are up to that standard that is necessary for the job, and then the second of all is so important to just document it, comment it with doc strings and comments. Really be super careful with making sure that whoever reads the code should understand exactly why the code is written in a certain way. So absolutely, I can't stress that enough.
Cool. So that's how you essentially transition to deep render, and now you're still currently, as I mentioned, working there. So let's dive into this. Like, first of all, what is deep render? You mentioned something around video compression, but what is it exactly? What is the company doing in a high level view, essentially?
Yeah, so deep render, what we're doing here is we're currently developing the next generation's media compression algorithms using neural networks. So, and media, what kind of media are we focusing on? We're mainly image and videos. I guess I will go in a little bit later on in terms of like why that is important. But it's a startup right now that was founded in 2017, which was roughly where sort of AI-based media compression kicked off in the research domain. So the two founders, Christian and Arslan, they saw the commercial potential of it around the same time, and started up the project, and started up the company. I mean, and then they 2019, as I mentioned, they received the seed funding and started to take on more hires and engineers and scientists. And today we're a group of 17 people who are all mostly, or most of all, of us are research oriented. So it's really just a kind of, I like to think, a research a research startup, or a think tank almost, that focuses on one specific topic, which is how do we solve the problem with compression. So what I do there, so I started out as one of the 3 research engineers, so the first ones in the company. I guess in a nutshell, what I do is we come up with lots of ideas during our brainstorming sessions, and which includes both the engineers and the scientists. Come up with experiments that we need to kick off, and models to train. So we'll code up these deep learning architectures, so these neural networks, and then we train them for a few days, basically. It's quite large networks, and then at the end of the day, we collect the results and we analyze them and discuss their implications and write up internal documentation. That's kind of like what we sort of on paper do. But I would say, since it's a startup, and at the time was a very small one, I remember like my job task was so different from day to day. Like one day I did a research sprint digging into, a kind of looking into a particular topic of compression and how to improve it. Another day I was writing a patent. A third day I was building workstations, and fourth day producing data sets or benchmarking our performance. So really varied throughout day to day. They kind of like threw me into any sort of task onto me that I was willing to do. And so so I guess as the team grew, I got more and more responsibility. And so I was promoted after my first year to a senior research engineer, and which entailed doing a lot more supervising roles. So I had a team as well that I was supervising, and got more involved in the onboarding process of new recruits, and also with interviews. So yeah, ultimately now in a position where I have gotten more and more ownership of the final pipeline, responsible for making sure that it trains, the full pipeline trains as intended, and we get the results that we want.
So why, like you mentioned this video compression using AI, but can you maybe explain why this is such a big problem? Why is video compression such, well, so important, and why do we want to compress videos? Like what's the goal here? What are you trying to achieve?
For sure. So maybe we can start with the idea of compression. So and I think really the main to start off like with compression in specifically for images. So you've all heard of JPEG, PNG, GIFs, and etc. You know, all of these type of files, these file extensions that you sometimes see on your laptop or your computer, and these are all compression algorithms specifically for those that deal with images. So I'll start with images because as we know, videos right now is just a stream of images. So it's just the next, I guess, this next layer of complexity there. But really, the principle of an image compression algorithm is to reduce the file size for the digital representation of that image without impacting or degrading the quality of that data. And so, because everything in the digital world is represented in bits, what we eventually want is a bit stream of zeros and ones that contain the information of that image, whilst keeping that bit stream as short as possible. So I guess a very intuitive example, super dumbed down, you can imagine you have an image of a blue sky, and let's say like a cloud in the middle somewhere. So instead of kind of representing them in terms of pixels, each pixel saying blue, 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 cloud, 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 blue, 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 blue for each pixel, on and on, you know, we can say start with blue, repeat for X number of pixels, and then you have cloud for Y number of pixels, and then a blue again for Z number of pixels. So this representation of that same image is much more compressed than having everything stored in its raw format. And that's effectively what we're trying to do. So, sorry,
just to interrupt you, why do you want this compression in the first instance? Like what's the goal? I mean, I get it, you get more information, but why do you want this compression? Why would it be useful?
Yeah, so compression today is kind of, I think of it as sort of, it's almost the invisible glue that keeps everything together in the internet age of today. And so I will throw out some statistics then around kind of what what we're dealing with, the scale of the problem that we're dealing with. So actually today we are we have 85% of the internet traffic consisting of visual media, and that is images and video. So the largest portion of information being transmitted across our network systems are just video, and most of that is streaming services like Netflix and YouTube and so on. And so thinking about the average compression ratio we have today, that is 20x for images and roughly 250x for video. That means, and these are compression ratios, which basically express how much are we actually compressing it against a raw format. So you can think of these numbers as being quite large, but basically it underpins the way that we use our network system today in a staggering magnitude. And so what's scary is that this 85%, this number is consistently rising. So only in recent years, you know, the quality of the streamed video has gone up significantly. I mean, I like to always use the example of thinking of if you watch a YouTube video that was posted 10 years ago. You mean you can barely see anything in it. Like it's very rare to encounter anything that was filmed that was stored in a larger resolution than 360p, you know. And so it's to us, like the way that the standard that we are used to, it looks like it's been filmed, you know, by a toaster. And so the today the content creation and delivery services like Amazon Prime, Disney Plus, Netflix, all of them are expected to deliver the high resolution content. You know, we're talking 4K, 60 FPS. We have emerging technologies today, such as VR, and all of these things really sets a new standard and new precedents on the quality of the content that people expect. And so people often fail to realize that there is a physical limitation on the bandwidth infrastructure that we have today. And I think the recent pandemic has been a perfect example of this. The amount of internet that we've used in 2020 more than doubled in the UK compared to the previous year. And so we've also seen the effects of the capacity not meeting the demand. Most of us has experienced, you know, working from home. If you work from home, you've seen connection issues during Zoom calls. When you try to stream something from Netflix, there's been annoying buffering at certain times, you know, especially during evenings when there's a lot of network demand at that point. If you're into gaming or live sports streaming, you certainly experience lagging in the connection. And so, and all of this really puts a huge strain on broadband providers, and which incurs huge costs for dealing with these network traffic surges. And so we're talking about costs of several hundred millions of pounds. And so let's say now that you have improved compression by 50%. Well, then what that means is that for the same visual quality of the data of the videos that you deliver to the end users, you reduce that data load by 50%. We could save broadband providers hundreds of millions of pounds every year. And so, and what it also would mean is that content would be delivered at faster rates to your homes, which means fewer interruptions, less buffering, increased productivity. And all of this is really, in my opinion, sort of even taken for granted. I think a lot of us don't kind of realize what's happening under the hood, and what's happening under the hood is pretty cool, actually. So, you know, that all of the compression has really kept us together for such a long time. And what's more is that, you know, the reduction in the bandwidth and the actual bandwidth use could also enable delivery of higher quality content to remote locations, which don't necessarily have access to high-speed internet services. I mean, of course, better compression means less storage spaces for which is quite valuable, I think, to have for cloud servers. This also has immediate knock-on effects for the electricity consumption of service and internet service providers, drastically reducing, you know, the impact on climate change due to the technology that we embed. So I guess, yeah, I mean, in summary, really, and I guess for the listeners who are into pop culture and especially the HBO TV shows, yes, we're pretty much like Pied Piper in Silicon Valley, if you've seen the show. But yeah,
no, I think that's interesting because I mean, when you're using your laptop, you're just watching a YouTube video or something like that, and you don't really think about, okay, how much, I don't know, information does this use? How does your laptop work? And things like that. But actually, I guess it's quite complex under the hood. You want to optimize the space that this video takes on whatever. I'm not very familiar with this problem, but yeah, basically compress the video as much as you can so that you don't need to send too much information to each laptop or things like that. So yeah, I guess that's like, if you just think about YouTube, that's already like a huge market, but it's not just YouTube, it's even bigger than that, I guess, because yeah, calls, like Zoom calls use videos. I mean, images, even in Google, use, right, the same algorithm.
If this Zoom call freezes between you and me, then you know what the problem is. Then then I need to go back to work.
Cool. So yeah, I think the problem is quite clear, and yeah, I see basically the goal is to compress an image, but can you maybe dive into like where AI plays a role there? Like, why do we need AI to compress this image?
For sure. So we need to talk about just quickly around traditional compression. What I mean by traditional compression is really fundamentally the sort of the type of algorithms that are employed today. So what do we use today? We're actually using compression algorithms that are founded in ideas that emerged in the 70s. And that idea really underpins the way that JPEG works. And so, so JPEG is a standard, is a compression standard that has existed since the 90s. It's again, all credits to that. It was quite a clever method back then, and it's worked quite well. And people, the video codecs that were developed in the 90s and the noughties, based on that technology, and we've seen a good increase in the compression ratios from that technology. But now the main problem with that, with those type of algorithms, is that they are experiencing a diminishing returns in their improvement. Mm-hmm. And so we have so the newest codecs that are out there, that have come out in the last decade, have only been marginally better than the previous generations codecs. And so you have this drastic slowdown in the development of this old traditional compression pipeline, whilst at the same time on the demand side, now you have exponential growth in the data. And so these two combined together equals absolute disaster for our network, our bandwidth, the bandwidth of the future. So what AI does, which is really good, which is quite interesting, is to completely reinvent the way the compression is done. So you have these traditional codecs that are mainly handcrafted, very hardcore engineered. They're people who have been tweaking numbers here and there, and then assessed how that impacts the pipeline. And really been working mainly with something that we call linear transforms. So linear transforms are a class of transformation that only deals with linear operations. And so what AI codecs can do that the traditional codecs cannot is to approach this through an end-to-end pipeline. And so what we mean by end-to-end is to optimize it through gradient descent, through a data-driven approach. And what this means is that we have, and we also know that neural networks are nonlinear, so they use activation functions which introduce nonlinearities in the function space that we're in. And so it's and since you're training it end to end, which means you can optimize it through with gradient descent, everything gets tuned at the same time. So you have the encoder module and the decoder module that understands what they need from each other. They have the gradient signals that backpropagate throughout both modules, as well as the probability model that you impose on it. And so it's much more flexible in that sense, and really can be approached through a complete data-driven approach.
Sorry, can you just describe on a high level, like without any mathematical explanation, what's the encoder, what's the decoder, like how does it work essentially?
Sure. So our compression model is as a backbone an autoencoder. And so an autoencoder is a type of neural network that is trained to output the exact same input. So it often consists of an encoder module, which is a neural network as well, that downsamples the input, which can be an image or a video, into a smaller representation, which we call a bottleneck space. We also call this a latent vector. And this small representation is often more compressible than the original data. So this is effectively the part that we would send out as a bit stream to between the users of the algorithm. And then you have the decoder module, which is again a neural network that takes in this latent vector and then outputs a reconstruction of the image.
Okay, yeah, that makes sense. And so you have an image, you compress it into some kind of smaller image or smaller information vector or matrix or whatever. And then you have the decoder, which takes this kind of smaller data storage thing, like smaller image or smaller information matrix, and decodes it to try to get back the original image, but with less information, essentially.
Yes, or let's say with less information that is required to represent that data. So it's there's a lot of mathematics that goes on here, and it was quite overwhelming to begin with, but it's fundamentally in its fundamental principles, everything is based on fundamental principles on information theory and probability theory. So and it takes quite a lot of time to get your head around it, but it's really cool once you have the overarching picture of how exactly it's working, both sort of like how it used to work in the traditional space and now in the AI space. It's really cool to kind of like draw those connections and see kind of exactly how it's doing the things that you want it to do with. And I should also mention one of the cool things is actually that I guess according to a lot of the guests that you've had, a lot of people have been emphasizing the role of data. You need, good data. You need accurate, clean data. Someone needs like the hours, the 80% that it does that machine learning is about. It's just to get the data clean, get it from a clean source and all that. We don't have any of those issues. And we're very, very lucky for that, because I think the problem is quite hard enough as it is. I mean, what we are doing is essentially compressing the images that are out, that exist in the digital world. So we just scrape some images together and then basically and then call it a day.
So the focus is on the algorithm there, compared to, you don't need to worry too much. You've got loads of data, which is of good quality. So you're really focusing a lot on this algorithm and making the compression as good as it can be to, minimize the information that you're going to send to users, essentially, and make streaming more efficient and everything you mentioned earlier.
Yeah, absolutely. It's all about it's all about the algorithms, really, and how to deal with the big problems of dealing with high dimensionalities and the probability spaces, and that's for those type of problems. And maybe I just quickly allude to one of the things around why AI might help so much with tasks like compression, and that is that our brains are also neural networks, and every second, every fraction of a second, we take in so much information through our eyes that amount to several gigabytes per second, and somehow our brains is able to compute all of that complexity and compress that into something that is smaller. We know that because we obviously have limited capacity in our brains. And so somehow our brains are actually performing really, really well at the job of compression throughout, I guess, evolution. And so that's why having a compression model that is powered by AI seems like the obvious choice to devise as a system in this regime.
Okay, I see. So where are you now in terms of the startup? Are you like currently, do you have the algorithm and it's ready to be sent? I don't know. Or are you still developing it? Like, at which stage of this research are you? Are you just at the beginning of the research, trying to find which algorithm will work best?
We are at, I guess, a stage where we are looking to commercialize. So we have right now a state-of-the-art image pipeline that can run in real time, and we are ready to which could be deployed really right now. And so the next step that we're doing is that we're working with or with the current step, I should say, is that we're working with a video compression pipelines that really is this same idea, but you're just adding the temporal component on it. And so so that increases the complexity and the problem a little bit, but not in the solution. So in this the same principles apply as for the image pipeline. And so you're just working with slightly larger complexity data, really. That's but obviously the same things apply there, the same rules apply. And so and we're quite excited for that stage as well, because obviously that's where the real money exists.
Okay, cool. No, cool. That's very interesting. And yeah, the startup looks really cool. The problem looks challenging. So glad to hear that you're enjoying it. Let's maybe finish the episode with 2 questions on your career. The first one is, since you've done this transition from engineering to data and AI, what do you like so much about AI and machine learning? Why choosing these fields?
Yeah, I think I think there's so much potential to come up with radical and revolutionizing ideas and processes and what's really cool about is that AI and computer vision that I work with, there's still the question is not really how to do it any longer, but where can we do it? And so I think there's so many hidden places on which you can apply AI onto. And I say this, for instance, coming from working with compression, which AI-based compression really started out as a concept in 2017. So when the first research papers started to come out, and that's when Deep Render was founded. And previous to that, I guess people who were really into the space knew that it could be applied to compression, but it really took off, that the commercial prospect of that really took off around that time. So, and I think there still are an abundance of low-hanging fruits in the space there to where AI can take a place. And yeah, I think it's got quite a lot of potential, and being in there, I think it's cool that you have there's a lot more thinking that needs to be done rather than doing particularly. It's just about it's ultimately about observing the needs and demands of society and thinking about how we can apply this new set of tools that are presented to us that really kind of emerged from in the latest few years, and find a way to apply them. And that obviously doesn't mean that you should just try and stick AI into everything. I think I'm very much an opponent of that idea, of that idea, but it's more about really thinking about in theoretically where it makes sense to apply these models.
Yeah, cool. I think that makes sense. I also like the fact that, as you mentioned, it's very new, so there are lots of things that you can explore. There are still lots of things that no one has done, and so lots of new ideas that are coming up every year or even every month. You always get surprised by some papers or things like that, which I think makes it very interesting compared to maybe engineering, where things are more well-defined. Obviously, you always have research, but there are some things that have been there for, hundreds of years and are here to stay. Whereas in AI, it keeps evolving all the time, which is what kind of really excites me.
For sure.
So let's finish this episode with one advice. Like, if you just had one advice for someone to progress in their career, what would it be?
So I would say remembering that we're humans, we are neural networks. We're all neural networks, whether you like it or not. We always have a brain. So just as neural networks have two different modes, one is the training mode, which is where the neural network is taking in new inputs and updating its weights, and the inference mode where it is just doing things. I like to say we should try to focus a lot more on the training. We should try to get our neural networks to be more in the training mode and keep learning, always be learning something new, always update your weights. It really is the development really stops once you start getting into that evaluation stage and keep doing the same thing over and over again without actually improving. So I would say, every day, if you have some time, learn something new, something that you've always wanted to know about. Google that thing that you've been asking yourself how it works. Ask a few questions that you haven't asked before, or turn things upside down. What happens if you change this for this, and so on. And so really just keep an open mind and stay informed and keen to learn more.
Thanks, and thanks a lot for this. And thanks for the episode. It was great to catch up with you. I will see you soon in London. But thanks a lot. Have a good evening and hope to see you very soon.
Cool. Thanks, Neil.
Thank you. Bye.